a lot.
Go ahead.
Yeah, first of all, so I would like to say that it's a pleasure that Robin and I, we can present that here, but there are already many more people involved, and probably I even forgot some people, so sorry to them. So yeah, we want to present the HS3, which is basically a currently still in development standard that should help to share statistical models in high energy physics. So yeah, you might think that is now this typical situation, right, where you introduce a new standard and there are many competing standards. But we hope that this is not the case and that we actually really need HS3. So as a science community in the recent past and maybe basically the past, the way we communicated our science was that we published papers, and there we had the plots and some numbers and so on. But during recent years, this open science approach got more important, and yeah, many experiments and collaborations try to open up their research, and I mean, especially CERN has a couple of things. So like this open data portal, and there's also HEP data where you can put additional data to your publications and so on. And yeah, I noticed there's even a whole CERN open science policy that includes yeah, multiple steps. So not only the data, but also the infrastructure tools and whatever. So I mean, what you can't directly see in this picture is the statistical models. So they are probably somewhere in the tools or in the source code or whatsoever. But we want to highlight that publishing the statistical model itself is also very important, because this can help you to, for example, validate and reproduce your results. So either by yourself at a later step, or other people, other groups can use your results. And that is also important for the second point that is raised here. So reinterpretations and combinations, that also aligns a bit with what I showed you yesterday. So there are often theory groups or whatsoever, they try to use different measurements, and it would be really nice if they have access to the full statistical model. And of course, yeah, if you publish your paper, it would also be very nice if you could publish the data and the statistical model. And yeah, also for archiving. So maybe read in your statistical model in 30 years from now. So and all of this would lead to much better reproducibility, and yeah, would be very good scientific practice, I guess. So why don't we do this? So, I mean, this is not a new idea, right? So more than 20 years ago, there was some kind of workshop at the at CERN. I don't know if any one of you attended this actually. So I don't know. But yeah, there was already the idea that experiments should give their likelihood, and yeah, that they should publish the likelihoods, and there was basically no disagreement. So yeah, more than 20 years ago, everybody said, okay, we need to publish likelihoods. So should be solved, right? But of course, there are some problems. So one of the problems is that the statistical models in high energy physics are rather complex. So we have large software stacks with, yeah, sometimes millions lines of code and whatever, large code bases, and our likelihoods typically also have a lot of terms in them. And then there's even the problems that there are a lot of frameworks. So basically each collaboration has its own framework, and in the worst cases, even inside the collaborations, there are subgroups that then have their own frameworks and so on. So that is also, yeah, very much of different tools inside the same collaborations that does not help. And yeah, so even within the same collaboration, it's sometimes not that straightforward to share your analysis with a different group. And so yeah, again, the goals that we want to pursue with HS3 is that we want to have a long-term readability and usability. So for example, I just picked one random paper. So that was basically the discovery of the weak bosons. That was in the late 80s. And probably they used something like the CERN program library, which was in Fortran. And I've never read Fortran, and I have no idea what's happening here. And I couldn't reproduce their results if I had access to the data. So that is something that we do not want anymore. What we want to have is we want to have a human and machine readable format, and that should be independent of any software tools. So the likelihood should not depend on the current implementation or your current language of choice. And that is, we want to achieve this by having a descriptive standard that basically, if you have this, yeah, the documentation for the standard, and you have a file to this, you could basically start and rebuild the statistical model in any language of your choice. So that, I mean, that sounds great. So what is the status of that? Or let's maybe look at what's the current status in HEP. So I mean, we all know the de facto standard in HEP is that you use root, and if you do a statistical analysis with root, you usually use the RuFit tool, which is very powerful and it has a lot of features. And yeah, basically everything that needs to be done typically in HEP is somewhere in there. And so the statistical models in RuFit are often called Ru workspaces, or that is where they're stored in. And you can then save them as a binary file in a .root file. And I mean, we've already heard that these root files, they are quite nice in some aspects, but they are not really easy to access and to read from with outside root. And what is usually or very often the case is that if you do an analysis, you will have some histograms, and then this hist factory type of class of statistical models is very, very famous in many collaborations at least. So, and that is what it basically looks like. So basically you have histograms, and you can scale the individual bins, or you can scale the overall, and you can modify basically your template histograms to fit to your data points. That is basically what is implemented in this hist factory model. And because this hist factory is so famous and so much used, there's a pure Python implementation of this hist factory likelihood basically, and that is called PyHF. And PyHF gained really a lot of attention over the last years, because I mean, people like to use Python as we know by now. And what PyHF also achieved is that they found a way to write human readable JSON files that contain their statistical model. So it's they really achieved that you can publish your statistical model. And that is also what was done, for example. So here's a paper that combines likelihoods from Atlas and CMS. I guess it was for a Higgs workspace. And that is a snippet basically from this PyHF JSON file. So the only downside is that this is currently restricted to this hist factory-like models. And that is, so basically with HS3 now we want to open up this to include further and possibly all statistical models that you could think of. I mean, that is not a very simple task. So here's a graphic I stole from Wouter that is showing a computational graph of such a Higgs combination workspace. And basically, your leaves are some individual variables, and then there are all these operations that you can do, and you can have higher level nodes where the functions of these variables and so on. So this can get quite complicated, and also the JSON files can grow then pretty much. So as we saw in root, we have these binary files, and in PyHF we have these JSON files restricted to hist factory. But I mean, in general, we know there are more nice software and tools like, I mean, we're talking now Julia, but there's also another Python package called ZFit that is also interested in this. But currently there's no standardized format to publish your likelihood basically. So that is when HS3 comes into play. So what we try now is that we develop a standardized format that is human and machine readable. So we will also have something like a JSON-like format. So we say JSON-like because we now focus on JSON, but we don't want to restrict ourselves to that because it's a standard. So in principle, you could also use TOML or YAML whatsoever. But all our examples are in JSON for now. We want to be software independent, and in the standard, we just want to provide the generic mathematical definitions of the different terms a likelihood can have basically. And from these specifications then that are given in this document right here, which is a draft currently, you should then basically be able to build your own implementations in the language or tool of your choice. And what we currently, of course, aim for is that we are fully compatible not only with PyHF and hist factory, but also with the full power of root. So all these root workspaces. And I've already linked here. So on the one hand, it's the HS3 overleaf link that brings you basically to the current draft of this specification of the standard. And the other thing is the HS3 GitHub page. So there are a couple of GitHub pages, and they don't currently contain the implementations, but there are issues and GitHub discussions where we basically still discussing the specific points of the standard. Right. So and now I guess I hand over to Robin, who will give you a bit more in-depth insight in the standard and the current status of the implementation in Julia.
Okay. Yes. I will now go over the more technical side of the HS3 standard for now. And what we do have right now is several components of the HS3 standard that make up our statistical models. And basically, it's just a flat structure with no specific order or anything, but just a collection of individual elements that can depend on each other. So, for example, if you take a likelihood, for example, that has, of course, to be depend on some distribution and also probably some data. But what you could also do with HS3 is just take some individual elements and just process them. So, for example, you could also have valid HS3 files just containing some function or distribution if you want to process just that. But for now, we have distributions, functions, data, likelihoods, which I guess are the most important ones. So then some specifications for our parameters, like the ranges and maybe some actual values. Then a field to combine all of these for complete analysis, and some metadata and other information you might want to include for your analysis. So how does this actually look? I will show this off using a simple example, as you have probably seen a lot of times, like with some exponential background and a Gaussian signal on that. And we will start with the general structure of such an HS3 file you would generate for this kind of problem, which is basically this hierarchical diagram. We start now with the analysis part of this, where we basically already combine all the parts. Here we can define the used likelihood for this analysis, the parameters we are interested in, and other specifications for the parameters like the ranges and domains, if you want to call it like that, or some specific parameter values you want to include in your analysis. You could also include, if you want to do a Bayesian analysis, you could also use some prior distribution if you wanted to do that. And we believe in this, we could actually define everything we need for automatic analysis. Now moving on to the actual parameters we want to include in that. We basically have two options. We can either, or both, define ranges of parameters called domains, in which we basically just give the range of these parameters. We can also define parameter point values, where we could give some starting values, best fit values, or whatever we might want to include in our analysis. We can also set values to be constant in this field if we wanted to. Moving on, now going to the actual likelihoods we want to include. These are, as I already mentioned, just options to combine some distributions with some data. And what I also want to show here is that we can include several different likelihoods in one file, which maybe shares some data, but with different distributions or something like that. We can also include auxiliary distribution, where the data is basically implied. But so here we can see some likelihood containing the complete model, but also some likelihood containing the just the background distribution if you wanted to. Moving on to the probably core part of this, the distributions component. On the left-hand side, you can see a snippet from our HS3 standard draft to show off how this is actually put down in the standard. And on the right-hand side, you can see the implementation in JSON then for two distributions. So each element in HS3 has a unique identifier or name, if you want, that just identifies this object. And then at least for the case of distributions and functions, some type to actually identify what this object is you see there. So for these exponential distributions, we would have an example over here where we have a unique identifier, the type, and then the two parameters we need for this distribution here, which then refers, you can see it here, there are two strings. These refer to some parameters which might be defined somewhere else. But you could also include, if that's what you want to do. Oh, okay. Just some numbers, if you wanted to. And like that, we have a lot of more distributions already included in our standard, which you can look up in our current draft, and you can also get involved there in our overleaf document right now, which is also very much still work in progress. Now, going to the current status in Julia. We started implementing a version of for HS3 in Julia. And Root also did this. Since Root 6.26, there's a preliminary version for these HS3 workspaces. The tool is called Root JSON Factory Workspace tool. And for now, we want to show that we can actually produce valid statistical models from Root into our HS3 JSON, then read it in with Julia. See that these are the same statistical models in both frameworks, put it out again and read it in again in Root to show really this round trip as proof of concept for this standard. But for now, we only focus basically on the green part there. The rest will hopefully follow later. And even more, I mean, that's the way to go since the statistical models lie within Root. So for now, we worked on some implementations of this, and for now I have to really focus on some physics results. So I really optimized this for my personal use right now, and rather than for really a standalone package that will be used by other people. And actually my deadline is in like 2 weeks. So all the performance improvements, the bug fixes, cleanup, and so on, that will follow at some later point in time. For now, we still have to do a lot of tests, and yeah. But the basic functionalities for reading HS3 files is there, I would say. And what I want to do with this is show the feasibility of like this proof of concept we can do with that. Even more, I'm focusing on the Atlas Higgs discovery workspace, mostly on the Higgs to ZZ2 for leptons decay in there. And that is produced by Roofwood. We produce this file with Roofwood and then try to read it in with our work in progress implementation in Julia. And what we try to do with that in this implementation is make use of as much Julia, the normal Julia ecosystem as possible. So like we want to have our distributions to be with distributions.gl, and the likelihood should come from density interface and so on. So the only exceptions to this are the HIST factory models. Instead of using the LightHF package, we basically built our own HIST factory interpreter for this implementation. And for now, most modifier types and constraints are already working, but still work in progress. And for the distributions, we want to mostly use distributions.gl, but we all know the Roofwood package is a lot larger than the distributions.gl package, so we need to include some HEP-specific distributions again. And we do that while orienting on Roofwood and using, for now, quad GK for normalization. Now to show off that this actually can work. to show off the workflow I use in the prototype right now is we use JSON3 for reading of these files, into dicts. We then build some in-memory lightweight wrappers we call specs, which are basically which are an in-memory representation. We use this for topological sorting. As I pointed out earlier, elements can depend on each other, so we need to find out the correct order of things, the correct dependencies. So we use topological sorting for that, create constructor functions for each element with that, and build up function chains out of it. And with those, we can then create actual Julia objects, like I mentioned, distributions objects for the distributions and density interface objects for the likelihoods and so on. In the code that would look like this, we would first have some read-in and specs generation. We then can create the analysis object if we have it defined using an identifier, choosing these analysis, and the sorting and all that's already in this element. And we then can interface this using the normal density interface. For example, log density off, we can just use the likelihood of this analysis and give it the necessary parameters to evaluate it. We can also do, or it will be possible to do, just select certain elements out of this analysis. So for example, if you just wanted to have one distribution, you can also just select that and create only that specific distribution or some other object you might be interested in. So now to show off that this actually works, we do that by comparing the likelihood we get produced in Julia and Roofit with each other. And we basically scan the parameters spaces for that. So we keep all parameters at some fixed value and only change one, and basically look at the likelihood values for that. So in blue, you see the Julia values, and in red, the root values, and then the bottom, you can see the actual difference between both values. And, oh, sorry. What can be seen is that there's obviously some deviation, but this is actually constant up to order of 10 to the minus 10 for the left parameter we can see. And on the right-hand side, you can see another parameter where we actually have agreement up to 10 to the minus 7 from these. And yes, I know this is a rather weird shape, and we will have another look into this, but still agreement up to 10 to the minus 7 in this. Now we can interface, as I mentioned earlier, we can interface this with various Julia frameworks. What you can see here is from my Atlas Higgs workspace, the parameters in this workspace on here. In gray, in the background, you can see the values Roofit gives for a fit with 68% confidence intervals used produced by Minuet2 and Minos. In the dark blue color, you can see confidence intervals I created using profile likelihood GL and optim GL. And you can see they match quite nicely, actually. But you can also use interfaces, for example, with BUTGL, do some posterior sampling, which you can see in the lighter blue color, and the credible intervals in this case. And just to sum up the next steps, we need to do cleanup, performance improvements. It's still a growing standard, as I mentioned, so we have to keep up with the growing, of course. We want to modularize and generalize the code a little bit more, need to do some more testing and some more example and this output. So taking a model from Julia out into HS3, we haven't looked at that at all at the moment. And that's one of the major things in the future. So
yeah, so as a summary, yeah, HS3 is this evolving standard, and we hope it will evolve even further. And preliminary versions are already available for root, and the Julia proof of concept implementation is there basically, and we now need to make this yeah, a nice package hopefully soon. HS3 is actually also part of this Iris HEP initiative, so we hope that it will be really a thing that the HEP community will adapt to. And yeah, as I said, so we are still a growing group, and even the standard is not fixed yet. So now is a very good time to get involved if you're interested in, and we still need to discuss certain features of the standard, and we still need to, of course, discuss how we will implement this in Julia, for example. So here are again the links to the overleaf to the GitHub, and we also have a CERN e-group. So if you want to join the mailing list, so yeah, thanks a lot.
Super, thank you.